Hello and welcome to section 11.2. This is a first recorded lecture for Calc 3, 2021. We're going to be talking about vectors today. Feel free, since this is the first lecture, I should say it, feel free to put this at 1.5 times speed. I might suggest turning the closed captioning on. It's not going to be perfect, but it at least helps me pay attention to what's going on, and it helps me understand the words. Anyways, vectors. One thing before we get into the meat of this, I wanted to suggest there's a video here called Vectors, What Even Are They? It's from the 3 Blue 1 Brown channel, more focused on the essence of linear algebra, but vectors is one of those topics that is going to show up here in multivariable calculus. It's definitely showing up in physics, engineering courses that you might take. It's going to be a big focus in linear algebra. It's one of those topics that just keeps getting rehashed by different teachers, and so you learn to do it 4 or 5 different ways. This is the multivariable calculus way. What we're going to do is just go through a few of the examples in our book and hopefully learn along the way. Okay, example number 1. Find the component form and the length of the vector u in R3, 3-dimensional space, with an initial point, or with the initial point there and a terminal point there. Boom. So we're finding this vector. Okay, we're going to call this vector u. And in order to find the components of a vector, between 2 points, you just take your terminal point and subtract off your starting point. So if we use this, and we're subtracting off -1, 3, -2, 0 minus -1 is 1. And actually, there are a couple different notations that we can use here. The first one, I'll use the angle brackets, but I'm also going to use the stoplight version too. So yeah, 0 minus -1 is 1, 1 minus 3 is -2, and 5 minus -2 is 7. So hopefully that is the vector in component form using the angle bracket notations. This also could be definitely written as 1, -2, 7 in stoplight form. Great. And if we wanted to find the length of this vector, well, we really have a bunch of different, components here that would move in the x direction, move in the y direction, move in the z direction. So all we need to do is use our distance formula, the Pythagorean theorem, to get the magnitude of this vector. So here, we'll call that u. And in order to find the magnitude of u, or the length of this vector, we take the square root of 1 squared plus -2 squared plus 7 squared. And we get the square root of 1 plus 4 plus 49. So that's 54. And we can't really reduce that much. So the length of that vector is the square root of 54, a little bit more than 7. Cool. Not so bad there. I think we're good. I guess one thing that I could say at this point is, if we wanted to take our vector u and turn it into a unit vector of length 1, all we'd have to do is divide by the magnitude. So if we divided all of these components by the square root of 54, then the vector u would be a unit vector. All right. Number 2, a ball is shot by a slingshot into the air with an initial velocity that has a vertical component of 64 feet per second and a horizontal component of 10 feet per second. Determine its velocity at time t, the magnitude of its velocity at the highest point of its arc, and the magnitude of its velocity just at the moment it hits the ground. Ignore air resistance, assume this, okay, so it starts off on the ground. Cool. Velocity at time t. Okay, so this is going to be a vector throughout this. Okay. All right, initial velocity is a vector where we've got 64 feet per second in the, no, I'm going to put that in the second one, sorry. 64 feet per second in the vertical component and 10 feet per second in the horizontal component. And we want to find its velocity at a time t. So we're trying to make a function v of t in terms of t. What do we need to do there? Well, theoretically, if we're ignoring air resistance, like we always, well, not always do, but most of the time do in math classes, then the horizontal component should just stay pretty cool. But the acceleration due to gravity is going to factor into the vertical component. The acceleration, and we can write this in terms of t, it's just going to be a constant anyway, but it's minus 32 feet per second squared. And so the velocity, if we take an antiderivative, would be negative 32 feet per second. Well, I don't want to write that down. Feet per second in the middle of this thing. Negative 32 times t, and then plus whatever our initial velocity is, which in this case happens to be 64. So here, I'll write it as v0, and then we'll fill that in. That at least gives us the vertical component of velocity. You know what I should do? Maybe, I don't know, all this notation is maybe a little bit confusing, but you know, this is the acceleration in the vertical component and the velocity in the vertical component. If we wanted to write that velocity as a vector now, negative 32t plus 64 would be good for the vertical component. So I don't know why I just wrote it in the horizontal part. 10, sorry, negative 32 plus 64, boom. That looks like velocity to me. It's at least a velocity vector. If we wanted to look at the magnitude of the velocity, all right, so this is all part A. If we wanted to look at the magnitude of the velocity at the highest point of its arc, that won't be too bad, because at the highest point of its arc, the vertical velocity would just be 0. So I mean, that would be 10 feet per second. And it would be in the horizontal direction. Okay, maybe that one, yeah, that was kind of boring. Uh, and then we look at part C, the magnitude of the velocity just at the moment it hits the ground. Interesting. Well, one way that I might attack this is realizing that, since we're assuming ideal conditions here, this ball is starting off at the ground and it's going to end at the ground. And the initial velocity that it starts with really should be the same as the terminal velocity when it hits the ground, because everything along that, well, will be symmetric. I guess, technically the vertical component would be in the opposite direction. But yeah, like the velocity at the terminal point, and I'm just going with, yeah, we'll go with the vector valued part of it. Would be 10 still, but negative 64. And finding the magnitude of that velocity is not too big a deal. We just take the square root of 10 squared plus negative 64 squared. That's big and gross. I don't want to do it right now. Boom. Let's open up a GeoGebra. We're in Calc 3, so we'll use a 3D calculator. All right, square root of 10 squared plus 64 squared. Take a little shortcut there, but yeah, it's just a little bit more than 64. 64.78. Come on. There we go. Feet per second. All right, and I hope that's right. Honestly, I'm recording this before classes start, and I really didn't even look at this. So I hope that I do this right, and if I do it wrong, I'll record the whole thing again. But I don't know, that makes some sense. Go feel free to, ask Ali any questions. Or I can get back to you the next day I see you. All right, moving on to example 3. Here we've got 2 vectors, and we are going to combine these 2 vectors in a linear fashion. The first one, we're just scalar multiplying u times 2, and then adding it to v. There we'll subtract, and here we're going to scale, u here. So this one's, I don't know, this is maybe a little bit boring. You might want to try and, pause this and just do it yourself real quick and then check up on the answers. I'm going to go ahead and just do them right now. And to save some space, I think I'm going to go stoplight form. Okay. 2 times negative 2, 2, 4 plus 3, negative 5, 1, negative 4, 4, 8. And 3, negative 5, 1, and we're adding them. So this becomes negative 1, negative 1, and 9. Cool. Moving on. 3, negative 5, 1, minus negative 2, 2, 4 equals 3 minus negative 2 is 5. Negative 5 minus 2 is negative 7. And 1 minus 4 is negative 3. Cool. Last one. We're finding the magnitude of negative 1/2 u. So, well, let's go ahead and just write that out and we can do it step by step. U again is -2, 2, 4. Cool. So -1/2. Well, let's do that multiplication. -1/2 would be 1, -1, and 2. And we still want to find the magnitude of this. So we're going to do the square root of 1 squared plus -1 squared plus 2 squared. And that's 1 plus 1 is 2, and then square root of 6 total. Okay. Great. Example number 4. Given two vectors, depict -2v and u minus v. Let's go ahead and draw this out. Since it says depict, let's draw. These are two-dimensional vectors now, which will be used in this class sometimes, more often three-dimensional, but let's go, u is in the pink. So we go 5, -2. So I don't know, roughly here. Oh, that was bad. All right, so 5, -2. And then v is -1, 2. Boom, boom. Okay, so -2v would be in the opposite direction of v and twice as long. And that would be +2, and then -4. Cool. And then if we did u minus v, really, I mean, let's see, what color? Purple. That means we would be traveling down the length of u, and then also heading down minus v. So I might, here, actually, let's make this blue. Not that anybody cares. All right, blue. Doesn't need to be blue, but we're fine. And then u minus v would look like this. And it would be 6 and -2 minus 2 -4. All right, so I didn't do a great job of making sure those hit the same y value. I need to make the green one a little bit longer. Let's see what we can do here. Movie magic. Oh, that's horrible. All right, fail. Let's keep going. But yeah, that vector, the purple vector, u minus v, can show up there. Also, if you wanted to view it as going from the tip of v to the tip of u, that is the same vector. And that's another way to kind of visualize it, especially if you're visualizing u and v as kind of making a parallelogram, like this. Kind of bad. U minus v is one of the diagonals of that parallelogram, and then v minus u would be the other diagonal. Or actually, just kidding. U minus v is that. V minus u would just be the other direction. But if you wanted to get the other diagonal of the parallelogram, you would add u plus v. All right. Example 4, down. Moving on to example 5. Given 2 points, determine the coordinates of the point halfway between P and Q and a quarter of the way from P to Q. Great. What we will need to do is find a vector from P to Q, and then we will use that vector to find halfway and a quarter. No big deal. And I guess we've got a GeoGebra thing. I'm going to hold off on doing the GeoGebra thing right now, but we'll look at it. Let's go ahead and just crunch the numbers. To make a vector v between P and Q, we want to start at the terminal point. Well, at least the terminal point comes first, and then we subtract off the initial point. And our vector v would look like 3 minus -2 is 5. 2 minus 4 is -2, and -1 minus 1 is -2. All right, so our vector is 5, -2, -2. And in order to get something halfway between P and Q, what we could do, the idea is start at P and add 1/2 of our vector v. So this halfway point, let's call it M, will be P. And then we will add 1/2 of v. So that would be 5 halves, -1, -1. And we should get a point like 1/2, 3, and 0. Hopefully that holds up. And if we wanted to go 1/4 of the way from P to Q, this wouldn't be, oh, I don't want to name it Q. I was going to name it Q for quarter, but let's call it R for quarter. Again, we would start at P, and the only thing that would change is, well, here, let me move this down because I should show you the general form of it first. But the idea is P plus 1/4 of V this time. So we've got P there, and 1/4 of V would look like 5/4, -1/2, and -1/2. So that would become -3/4. 3.5. So 7 halves. I don't know why I'm going all fractions, but I am. And then 1/2. Great. So let's see if I click on this GeoGebra and things turn out the way that I'd hoped. Hey, we've got a good vector there. So let's take a look at what GeoGebra does here. What I've done is put in P and Q. And if I tell it to go Q minus P, we get this vector V, and notice that it automatically puts at the origin. And if we want to translate it so that it starts at P, we can go like this, and that's fine. What I've done here is I made a vector that is scalable by this scalar T. This is the one at the origin. This is the one at P. So if we want to find the coordinates of the point at the end of here, it should work out. If we make this 0.5, we hopefully get something very different than what I wrote on the other page. Oh, what did I do? No. Oh, we're good. We're down here. Okay. 1/2, 3 and 0. That is what I have here. I'll show you. 1/2, 3 and 0. We're golden. Sorry. And then if we want to just go 1/4, let's type it in. 0.25. That's taking our p and adding on the scaled version of, q minus p. And there we get the -3/4, the 3.5 and the 0.5, just like we had before. Cool. But I like looking at this because it visualizes it. Okay, moving on. Example 6, and then we got 7, and that's pretty much it. Those are the homework questions. Okay, so 2 more. Example number 6. Let U be this. Express U as a linear combination of the standard basis vectors of R3, and also express U as the product of its magnitude and a vector pointing in the same direction. So I don't know if I've already introduced you to I, J, and K, but or I hat, J hat, and K hat is, I guess, what I'd like to normally say. But yeah, those are the standard basis vectors in the X direction and the Y direction and the Z direction. And so if we wanted to express U as a linear combination of those vectors, what we could do is just say U is 3 times I hat plus -2. Why don't I just do -2 times J hat and then +4 times K hat. No problem. We got it. That is a linear combination because it is scaled versions of these standard basis vectors. And it's a linear combination because we've just added and subtracted them together. That's great. Cool. For part B, it asks us to express U as the product of its magnitude and a vector pointing in the same direction. So we want to turn U into a unit vector so that we can multiply it by its magnitude and get U back to where it was. So first things first, let's find the magnitude of U. Square root of 3 squared plus -2 squared plus 4 squared. Square root of 9 plus 4 plus 16, 29. Cool. And in order to do this, we would just need to have the square root of 29 out here. That's the magnitude. And then multiply it times a unit vector. And the way that we create the unit vector, I know this is kind of silly, but we would have 3 divided by the square root of 29, -2 divided by the square root of 29, and 4 divided by the square root of 29. And again, if we wanted to, look at that and make sure that things are the way they should be, we could look at it on GeoGebra. I think I'm gonna skip that for now. So yeah, this part is the unit vector. Cool. And there's scalar multiplication as an operation between those two. All right, example number 7, the fun one. The one that you will do many more of if you are a mechanical engineer. A 10-pound weight is suspended from 2 ropes, as shown in figure 10. The ropes are different lengths, so the tensions and forces, T1 and T2, in the ropes are unequal. Given the measured angles shown in the figure, determine the tension vectors. Okay, so the idea here is I'm drawing, I think, what's kind of like a free body diagram, at least a mathematician's version of a free body diagram. We've got our weight vector hanging down here, and T weight, I don't even know if I want to call this T. Let's just call this big old W, because it's not really a tension force. You just got the weight of this 10-pound thing going on. And the vector that I'm going to assign to it is just 0 and then -10, because it is pulling 10 units down in the Y direction. Now, yes, if I'm a mathematician, what I'm doing is situating this whole thing in a coordinate plane, and I'm probably looking at this portion right at the top of the weight as kind of our origin, and viewing this as an X and Y axis. Let's see how this goes for us. So yeah, this weight would be pulling with a 10-pound force down. That's why I've got that there. Now let's take a look at the other forces. Since we have a 25-degree angle up here on T1, we would have another 25-degree angle down here, because they are alternate interior angles of two parallel lines. If I get really sneaky, yeah, these are two parallel lines with the new x-axis that I just made and this hopefully flat ceiling or whatever we're hanging from. So we're, assuming those are parallel. What I'd like to do there is, since we know the 25 degrees, we can situate the direction of the vector, but right now what's unknown is the magnitude of that vector, because we know that the tension 1 and the tension 2 are sharing the overall force of this weight, but we don't know exactly how they're sharing it. So what I'm going to do for now is write the magnitude of T1 as kind of an unknown. And then we want to multiply that times a unit vector. The unit vector in this case could be given to us by using the unit circle. Here we are pointed there with 25 degrees before we hit 180 degrees flat here. So we would do, it's the opposite of the angle if we were looking at a 25-degree angle over here. The x component would be in the opposite direction. So I'm going to go ahead and write negative cosine of 25 degrees. And the y component is still the same as 25 degrees. I could have gone to cosine of 155 degrees and sine of 155 degrees, but this is a nice smaller angle. So yeah, maybe we do this. Okay, and so there's our unit vector. Since we're just using sines and cosines of the same angle, yeah, that's actually going to be guaranteed a unit vector by the Pythagorean identity. I mean, you guys could try this out if I haven't shown it to you already. But like, remember, I don't know, cosine of an angle squared plus the sine of an angle squared, whoops, equals 1. Yeah, that's a big deal, because you end up, I mean, for the distance formula, think about taking the square root of each side. It's still 1, but yeah, there you have the distance formula on the left-hand side. So magnitude is always going to be 1, and that's great. Cool, unit vector. Moving on to the second vector, tension number 2. Here again, we've got I don't know, we've got a 60-degree angle because of alternate interior, and this one's even easier. Let's go and make the unknown magnitude of T2, but we're going to multiply it times the unit vector where we've got cosine of 60 degrees and sine of 60 degrees. Cool. So once we've done that, I'm going to scoot us over just a tad. We need to think about how these vectors are related. In order to support this weight and keep it stationary, the top two vectors need to add up to be the opposite of W. Or really the way that you might want to think about it is that the forces T1 plus T2 plus W equals a zero vector. And that would mean that it's stationary. So yeah, the idea here is that, I mean, we could write it out in a vector equation, but essentially what we have is an equation. Well, it's a vector equation with two unknowns, and we could treat that as a system of equations with two unknowns. Cosine of 60, sine of 60, and then plus W, which, sorry, is 0 and -10. All of that should equal zero vector. Oh gosh, all right, I'm off the screen. Sorry, let's go ahead and scooch over here. We get this vector equation. We're just trying to figure out if we scale T1 and we scale T2, what scales of those will eventually add up to be the opposite of 0, -10. So how will they end up adding up to 0 and 10? What we can do is tease those apart a little bit into two separate linear equations, two variables, two equations, and then solve that using elimination or substitution or even row reduction if you know how to do that with the matrix. But in the end, we get two tension vectors that look like this. And I already had that written down so that I didn't have to actually do that during this time. Okay. So the idea is set up this diagram, realize how those vectors need to be in relationship with each other in order to have a stable equilibrium, and then find out the tension vectors. Cool. And let's go ahead and see what we've got here on GeoGebra. Yeah, we've got a 10-pound weight here. A and B. Oh, cute. Well, there's not a bunch of stuff for me to click right now, so we could do it, but there's part of me that doesn't want to right now. If you want to, I can do this later. Actually, it's going to be part of the activity, which will be fun. We're going to do something very, very similar. Where am I going? I need to go back to OneNote. We're almost done, so I want to get there. Oh, this is actually the homework stuff. So here we're expressing W as a linear combination of U and V. So you'll be doing something very, very similar to what I just did here. You'd have the overall equation, W equals something times U plus something times V. And you could solve that by elimination, substitution, row reduction. But that's cool to learn about linear combinations. And this last one is about a jet liner flying at 600 miles per hour due west, encountering a headwind. And what you have to do is, account for that wind that's blowing in at an interesting direction to increase the speed and steer in a direction so that they would stay ground speed going at 600 miles per hour due west. So that's a cool problem as well. Other than that, I'll see you for your next class. And yeah, please go ahead and discuss things. You have any questions? All right, talk to you later. Bye.